But Atul will today tell us about some very interesting results and challenges that dot the landscape of secure quantum computation over classical networks. So Atul, whenever you're ready, the floor is all yours.
Yeah, thanks a lot, Ramanujan, for organizing this talk and for introducing. And thanks, Tom, for inviting me to speak about my recent works on secure quantum computation over classical networks. So in this talk, I'll mostly split the talk in two halves. In first half, I'll cover a brief landscape in last 2 decades over what happened in delegated quantum computing. And the next half, I'll talk about recent results um, in this direction. So let me start with the yeah. So in one line, if I have to say like a difference between classical and quantum devices, is like classical devices cannot efficiently simulate quantum systems. At least we believe this. And so although recently, or like the field has been moving from scientific curiosity to actual realization, and there has been a lot of important milestones over the years. So in terms of secure communication, there have been a demonstration over 7,000 kilometers in 2017 between China and Austria. And also entanglement-based secure quantum cryptography over 1,100 kilometers has been demonstrated. And more recently, Google and China have demonstrated quantum advantage in superconducting systems and photons. So these are like really amazing feat. And so that means building quantum computers is definitely very hard, but not probably impossible. And hardware is working, so we need to, from theoretical point of view, we need to think of what's next. So in this direction, I'll mostly speak about finding applications for quantum internet, and this is also my research direction so far. And basically, quantum internet promises to provide radically new internet technologies. So some applications may not be even possible to accomplish on the conventional internet. And just to give a brief idea about the functionalities that we can implement over quantum internet, it depends on the different stages of quantum network. So the lowest is if we just have trusted repeaters, which we can implement quantum key distribution, and the higher we go over the ladder, if we have if we have nodes over quantum internet that have full quantum computing devices, then we can implement redirections, and even with the small quantum memories, we can implement many interesting protocols. So definitely, quantum internet is not going to replace all the classical internet, or it's very unlikely, but a more realistic setting or near-term setting is where both quantum and classical channel will coexist. And we would like to minimize quantum resources so that we can efficiently utilize both the resources. And in this talk, I'll talk about a killer application of quantum computing, which is this blind quantum computing. So let me talk about the setup. So this is a two-party problem where we have a user on the left-hand side and a server on the right-hand side. So user is limited by computational resources. So maybe she has a very weak quantum device, or maybe not even any quantum devices, or just classical devices like phone, mobile phone, or computer. And she wants to use a quantum computer to solve her problem, but she doesn't want to reveal the data. And so we want to perform cloud quantum computing. And on the other hand, server has a full quantum computer and is willing to help and provide cloud-based services, maybe with some payment. But of course, it cannot be trusted. So the problem definitely boils down to two flavors, which is blindness, where we want to guarantee privacy of client's computation. And on the other hand, we also want guarantees on the correctness of outcome. So in the first setting, this is also known as blindness or blind quantum computing, where the only guarantee is that client's computation or data is hidden from the server, and no guarantee on the correctness of the outcome. And on the other hand, in verification, we would like a client to verify that the computation server has performed is indeed correct. So in this talk, I'll mostly talk about the blind quantum computing setting where we only care about hiding client's data and not about the correctness. So ideally, what we would like from such a setup is we would like a large class of computation to be possible. So maybe a universal class of quantum computations. At the same time, we would like to have a very high level of security. For example, there are two notions of security: information theoretic versus computational. So by information theoretic security, I mean we would like to have security against computationally unbounded adversaries. And computational security means we would like to have maybe adversaries who are quantum polynomial time bounded. So in this talk, I'll talk about both the protocols which achieve different kinds of security, and in particular, information theoretic and computational. On the other hand, we also have securities which are standalone and composable. And by standalone, I mean protocols which only run once or in isolation. And composable means protocols that are run in arbitrary environment or in as a subroutine to other protocols. And at the same time, we would like to have design of these schemes which are modular, and so we can optimize for different resources. We would like to minimize the quantum resources or classical resources and interaction randomness. Similarly, we would like to minimize the round complexity of the protocol. And ideally, we would also like to have verification on top of it, so that in the end, the client can verify whether the computation has been produced correct or not. And so classically, we know that such a setting has been studied in 1987. And basically, there's a no-go result that computing NP-hard functions securely results in a polynomial hierarchy collapse. And so this problem is in information theoretic setting. So here, the server is unbounded. And what does intuitively that means is that functions that are harder to compute are also harder to encrypt. And this seems more or less correct, but in the quantum regime, we will see that this intuition doesn't hold anymore. But there are also simplifications of these schemes where we only care about computational adversaries, and these settings are computing over encrypted data. So there have been a lot of recent works under the name of fully homomorphic encryption schemes where such schemes are possible for delegating arbitrary computations to the server, assuming learning with errors and other problems. So next question that we would like to ask is what happens in these settings for quantum functions? Can we delegate quantum functions securely with information theoretic security? Or if not, can we do something with computational security? So let me take a brief introduction to quantum computing. So basically, what we in quantum, what we have is instead of bits, we have qubits, and instead of gates like and, or not gates, which are universal for classical, we have unitary gates. And instead of reading the output bit, we measure the final state and obtain a classical output. So just to give an example, for single qubit gates, we have Hadamard, which creates superposition when performed on computational basis states. And then we also have 2 qubit gates or entangling gates, which are like C0, for example, and control Z, which is also written as CZ. So these create entanglement between 2 qubits. And these can also be seen as if and then operation. So if the first qubit is in 0 state, then it does nothing to the second. And if the first is in 1, then it flips the second qubit. And so just to quickly recap, the notations that I will use is for single qubit states, I'll use this cat, which are like two-dimensional vectors. And in quantum, we can also have superpositions of these computational basis states. So here, alpha and beta are not just the positive coefficients, but they can be negative or even complex. And they are like, they are also known as amplitudes. And so the only conditions that we want is that the square of alpha and beta squared should be 1. So the probability should be normalized. And similarly, we can write the n-qubit state with coefficients alpha x. And once we measure this state at the end, we obtain the classical output string x with the probability alpha x squared. And also we want again, the probability to sum to 1. So it should be a unit vector. So just to give an example, how do we combine these different gadgets is we initialize the input state, we apply these single qubit and 2-qubit gates, and we obtain output state. So for example, if I use a header mod from this left-hand side and control node on these computational basis states, then the output would be entangled state. So this is an entanglement creating circuit. So, and just to recap the circuit model, which is quantum circuit model analogous to a classical circuit model, is we prepare a quantum state in the computational basis state. We apply a sequence of unitary operations and perform measurements of one or more of the qubits. So for example, this is one of the circuit where we initialize the qubits. We performed some operations and measured some of the qubits to obtain our result. But on the other hand, there is another very interesting computing model, which is also known as measurement based model. And this apparently has no classical analog. So what happens in this measurement based model is a computation is performed by means of single qubit projective measurements instead of unitary operations on a highly entangled state. So basically we have, so by highly entangled state, I mean something like this graph state. So this is a compact way of representing a entangled state where each of these nodes is a qubit and this edge is a entangling operation. So this is a 5 by 5, so 25 qubit entangling state. And this Pac-Man symbolizes some single qubit projective measurement. So it's, and there are no unitary operations. And still this measurement-based model is equally powerful as quantum circuit model. And this is something very non-intuitive. So just to give an example.
Does it have to be on the full grid?
Sorry?
Like, do we have to consider the full grid?
No, so this is just a universal resource state, but you can have very specific resource states. Like, yeah. So this resource state is also called as cluster state. And just to give an analogy, so if circuit model, if the computation is like making a sculpture, then circuit model is like adding stone by stone to make a sculpture. On the other hand, measurement-based model is something like you take a huge rock and you just carve out your desired computation, and both will lead to your desired sculpture. It's just that maybe you would require a lot of resources for this. So basically they're equally powerful, except that maybe you need polynomial overhead resources to do the computation, the same computation.
So there is like a simulation theorem saying that you can go from one to the other?
Yeah.
Okay.
So basically what all you require in this measurement-based model is a very highly entangled state and measurements. And the most important part is the measurements have to be adaptive. That means, for example, in this Pac-Man, if the current measurement that I'm performing is on this 8th qubit, then this might in principle depend on the measurement outcome of the previous 7, like some of the 7s. So you cannot just perform all the measurements on all the qubit at once.
And POVMs and stuff like that are disallowed?
You can, but since single qubit projective measurements are sufficient to do any computation, you don't usually go higher, but you can do it. So initially people started with 2 qubit measurement, and then they realized that even single qubit is sufficient.
Thanks.
So So yeah, so this model has been very useful in delegated quantum computing. So we'll see how we can use this. So I'll just quickly go through some of the primitives that I will use later. So one is quantum no cloning theorem, which says that there cannot exist any physical device like this box, which takes these two inputs, psi and phi, where phi is an auxiliary state, and output two copies of psi in general. So the psi is an unknown quantum state. So such a kind of box is not possible even with unbounded power. So this is just limited by information theory. And this principle has been used initially in quantum cryptography for proving securities in quantum key distributions and quantum money, etc. But in this talk, we'll see security limitations of these two-party quantum cryptographic primitives that are limited by this no cloning theorem to achieve higher levels of security. So let me quickly go through very interesting primitive in quantum, which is quantum teleportation. So it's a two-party setting. Again, there are Alice and Bob, and they share this entangled state, which we created initially. And Alice shares some unknown state, psi, which she wants to send it to Bob. But she only shares a bell pair, and they are spatially separated, so maybe on different planets. So how can she send the state is she can perform some quantum circuit, which I'll just call Bell measurement, which comprises of the C0 and Hadamard and this single qubit projective measurement. And then she can classically communicate these measurement bits A and B to Bob, and Bob can apply some decoding operations to actually obtain this unknown state. And so here these metered boxes are just, you can assume as a function which takes a quantum state and outputs a classical bit. And why we are talking about quantum teleportation is because it also can be related to quantum one-time pad. So basically, let's see this scheme again, just the state before Alice communicated classically A and B. So if one computed, the state is basically this poly is applied to the state that Alice sent. So if one writes this in terms of density matrix, which I didn't write it, but so if you try to compute the density matrix of this just before the classical communication, then you'll realize that the density matrix, since Bob doesn't know A and B, it sums up to identity over 2. That means Bob has no information about psi at this point of time before the classical communication. And this also somehow preserves the relativity. On the other hand, in a quantum one-time pad, we have Alice and Bob who shares a key, A and B, and Alice wants to transmit a message psi securely to Bob. And so how does she do it? Is she applies the same operations that are visible here. And the good thing about these operations are that the square of these operations is identity. And so basically, if Alice applies ZAXB to psi, and Bob again applies ZAXB to this psi tilde, then it will decrypt it. So and this psi tilde is exactly the psi tilde here. So if any eavesdropper who doesn't know A and B, so secret keys, this would look like a completely mixed state. And so this quantum teleportation can also be seen as a quantum one-time pad scheme if you don't communicate classical communication. And so we have the same two properties, which is correctness. So Bob can read the message because he shares A and B, and because of this decoding ability. And for security, Eve gains no information because the state is completely mixed and independent of the message psi. So there is a similarity here. And again, on the left-hand side is the same quantum one-time pad figure. And just to give an idea of why quantum one-time pad is actually a one-time pad is you can see a generalization here. So let's say we want to encrypt a message M, and B is our randomness. So in classical one-time pad, we will just XOR it. And for decrypting, we'll again XOR back with the same random bit B. And how can we do this with the quantum states is we just apply this XP, which is a NOT gate. So it just flips it depending on the value of the B. So we encode M in the quantum state. And because of this property of X, we can see that this is exactly like a classical one-time pad just on the quantum states. And so X is a one-time pad in the computational basis state, and Z is the one-time pad on the Fourier transformed basis, so header-mount basis. And so basically quantum one-time pad is bit flips in both bases. So you require 2 bits. And we can see why we had A and B here to fully hide a quantum state. So, okay, so let's use these all these primitives for a scheme which is very well known in quantum, which is by Broadbent, Simons, and Kashefi. It's also known as Bfk scheme. So this is an unconditionally secured scheme. So unlike classical, we have a perfect security. And so and this is based on measurement-based model for quantum computation. So Alice's computation is written in terms of this graph state or this resource state, which has like n times m qubits. And the measurement is parameterized by these angles alpha. So this is some set of angle alpha. And Alice wants to compute. So basically this represents her computation. So if she can hide alpha, because this is a universal resource state, so she doesn't have to hide anything in this. So if she can hide alpha and still get the computation, then she's done. So how she can do it is, I'll give a very high level sketch of this. So she actually uses the quantum one-time pad. So she sends quantum states and keeps the key on her side. Bob uses this one-time pad states to prepare this resource state. And then she uses these key to actually hide the alpha in this updated angles, which are this represented by Pac-Man. And then she communicates these updated angles to Bob, and Bob performs this measurement on each of these qubits with this Pac-Man. So this updated angle is hiding alpha with the same key that is already sent via the quantum one-time pad. So basically, you somehow decrypt the randomness that you added before by this one-time pad. And this intuitively gives you a correctness. And on the other hand, because of the quantum one-time pad and one-time pad property, we also get security. So Bob, on each measurement, he obtains this 1 bit. He sends this 1 bit to Alice. And since in measurement-based quantum computation, the measurements have to be adaptive. So Alice will then use this 1 bit to adapt the measurement angle. So there is a function which is like one-time pad and depends on this 1 bit to compute this, this updated angles. And so there is a one-time quantum channel because she has to send this n times m qubits to Bob. And at the same time, there is a like nm rounds of classical interaction. So basically, this scheme consists of quantum and classical interaction, and the leakage is only this n and m, and which is minimum because a quantum server would definitely know what are the resources being used on their side. It's like the depth and the number of qubits being used. And just these are like the single qubit state. So this is also very minimum requirement on client side. At the same time, we get both the security as well as correctness. And this is information theoretically secure, so independent of the computational power of server. And this last layer is the output in case she wants a quantum output of the graphs. So basically, just to quickly summarize, so this field started in 2001, where Andrew Child studied this question of secure assisted quantum computation. But the scheme was with a very powerful quantum client, which required quantum memories and two-way quantum channels. And then in 2009, there were schemes by this Bfk scheme, which reduced the power on the client to minimum, or like almost minimum. Then we also have in 2012 schemes where a classical client can delegate computation to two entangled servers, but they're non-communicating. So the scheme was mainly for verification, so MIT solved, but it also had a delegation protocol. And in 2013, we studied the optimality of these schemes, whether these schemes are optimal with respect to quantum communication or not. And we gave a general upper bound and lower bound for different capabilities of quantum client. And we showed that BFK is an optimal scheme in this setting. And then so far the scheme, so far all the schemes until 2015 were either required client to be very weak in terms of quantum powers, but at least some quantum devices were required, or we required two entangled servers with non-communicating setting. So there were some limitations in terms of practicality. So ideally, what we would like is a completely classical client who can delegate the computation to quantum servers. And in 2016, we gave a first scheme that is again using a very strange facet of measurement-based quantum computing to give a classical client single server scheme. But apparently this is only statistically secure, so not perfectly secure. And we could not show the class of computation to be BQP. So this is still an open problem. But this is all these results are in information theoretic security. So maybe any questions so far? Or if I'm going too fast?
No, it seems like we are great.
Okay, awesome. All right, so basically what we want is, can we dequantize the quantum interaction from this BFK scheme? Because that is what we actually want to achieve. If we can dequantize it, classical interaction is still fine, but we don't have quantum channels at the moment. So in the rest of the talk, I'll give some progress in this direction on how we can dequantize the quantum interaction, and also some limitations of what kind of security we can achieve. So to do this, let's take a look at a cryptographic primitive known as remote state preparation. So what it does is, it's a two-party primitive. It outputs classical bits on Alice's side and outputs quantum state on Bob's side. And so basically, if you look at A and B for different values, we can see that, let's say it gives one of these four states. So either 0, 1 or plus minus. And this kind of primitive, we can already see that this is sort of what we want for a BFK scheme. So how we can realize this? It's easy to realize if Alice and Bob share quantum resources, because Alice could just perform quantum teleportation of this state. And then she would get these A and B. Or otherwise, if they share a quantum channel, she could just prepare this state and send it, which is what happens in the, again, the BFK scheme. Another way to realize this is if we have a quantum satellite, which spits out this classical bits on one of the locations and quantum states on another location. So this would be, since these states are independent of the computation that is performed, this is some kind of Beaver's triplet correlations setting. So it might not be easy, and it's also only secure as long as we assume that quantum satellite doesn't collude with Bob during the computation. But what if Alice and Bob only share a classical channel and they don't trust quantum satellite? So this is the kind of question that we want to aim at. Can we achieve this? So definitely we cannot achieve this information theoretically, because Bob can just, if there's any information theoretic secure protocol, Bob can just do tomography and get the state. So the only hope is to have some sort of computational security. So we want to put a leash on this quantum Bob. So just to give what are the results that we know in this area. So in 2017, there were a generalization of this classical Abadi et al. Scheme by Scott Aronson and all, where they showed that delegating BQP computations to a quantum server seems unlikely. Although this is an Oracle separation, but still it seems very hard to find a problem, hard to find a protocols which would prove delegation of quantum computation using only classical channels. And then these were the results that were based on perfect security. And in 2018, we have like fantastic set of results by Urmila Mahadev, who showed that quantum fully homomorphic encryptions for on classical channels and verification of quantum computations, again, only on classical channels. And these are based on learning with errors. So from here on, we have seen a lot of progress on the computational setting. And then in 2019.
But this is not information theoretic, right? This is like,
so from now on, like 2018, most of the progress has been on the computational side. So these are based on learning with errors problem. So we assume that it's computationally bounded. And then using the similar set of functionality which has been used in these protocols, there have been protocols for secure remote state preparation. And then in 2020, we showed the applications of secure remote state preparation to delegated quantum computation. And we also showed that there are some security limitations in the sense that it cannot be composably secure. And also we showed so I'll talk in detail about these works. And then also we showed how we can use secure Rsp and a variant of Bfk scheme to give a first quantum two-party computing that is based only on classical channel. So far, all the quantum multi-party computations or quantum two-party computations rely on quantum channel. So the rest of the talk is based on computational setting. So I'll assume that the security is only against quantum adversaries or quantum polynomial time adversaries. And I will cover quickly the last three results, which are based on secure Rsp and their applications. So just to give a high level overview of the Rsp construction, so there are two types of functions that are used. So one is using this trapdoor claw-free functions, and the other is using this homomorphic trapdoor injective one-way functions. And more or less the goal in these using these functions is to create functions which are one-way, are hard to invert, are also 2-to-1. And by 2-to-1, I mean for every image, there is exactly 2 preimages. They are collision resistance. That means it's very hard to find claws or pairs like this x and x prime, such that f of x is f of x prime without the trapdoors. However, with trapdoors, it is easy to invert y and find these claws. So we want to achieve more or less these kinds of functions with some additional properties, but it turns out that both these kinds of functionality is sufficient to achieve this. And so in this talk, I'll quickly tell you how we use this function to achieve this Rsp. So again, to remind you, the remote state preparation functionality spits out a classical description of the quantum state on the left-hand side to Alice, and quantum state on the right-hand side to Bob. So what we want is Alice generates this, the key and the trapdoor, which corresponds to these functions fk. and these are generated with these functions gk, which are trapdoor, injective, and homomorphic one-way functions. And another property of them is we can construct a hardcore predicate with respect to these functions. So hardcore predicate is only used to mostly used to show security in this case, whereas most the same function fk, which has the properties that I just showed in the previous slide. So what Alice wants to do is she would run this key generation algorithm and would send this public parameter k to quantum Bob. So now Alice and Bob only share a classical channel. So the first step that quantum Bob would do is he would prepare superpositions over all the inputs x, so over the domain. And then, so by preparing superposition, he just applies Hadamard over the domain. And then he evaluates the function f in another register. So this is a controlled f, a unitary that depends on this classical function. And this is known to Bob, given k. And then Bob measures the second register and obtains the image y. And corresponding to this, since this function is 2 to 1, the state would be collapsed to the two preimages, x and x prime, corresponding to this y. And then Bob would perform this function h, which is also public, and would measure all the qubits except the first one. And it turns out, and then Bob would send these classical outputs y and z to Alice. And the state on the last qubit is exactly this HAXB0. While on the other hand, Alice would use the trapdoor along with y to invert to get the preimages x and x prime, and would use z to obtain this a and b, which is only known to Alice because only she has this trapdoor key, whereas Bob doesn't get any information about the state that is being prepared. So this is, and the security is basically the bit A is the hardcore predicate. So this is chosen before the start of the protocol, and which implies that Bob cannot guess the bit A any better than probability half. So just by randomly guessing. And so this is the best one can hope for. The bit A is actually the basis bit. So if A is 0, then this is a 0-1 basis. And if A is 1, then this is a plus minus basis. So
I think I'm not fully following. Can you say this a little bit more regarding like the intuition behind like the protocol?
Yeah. So basically, here when you perform this controlled operations, you have a superposition over all the. So you have all the clause and all the y's corresponding to it. And once you perform a measurement, you collapse into one of the image. And since this is a 2 to 1 function, for every image, there are exactly 2 preimages.
I see.
So that's why basically you need the underlying 2 to 1 property here.
Okay, thanks.
And you can also achieve this using this trapdoor claw-free function. So this step is same for all the protocols. So for verification protocol or for certifiable randomness protocol, this step is same under. So it's just that this U of H is now used to somehow compress the randomness for all these qubits into this, the last one to give a RSP protocol. And the security follows from the hardcore predicate of this bit A. So this was, so this is the security only in the standalone model. That means only if we run this protocol once and in this game-based definition. Whereas what we want is, we want to use this module. This module on itself doesn't seem very interesting. So we want to use this module for in bigger complex cryptographic protocols like BFK or verification protocols. And so we want to study the composable security of this protocol. And by composable security, I mean we want to analyze the security of protocol when it is run in an arbitrary environment or in parallel to other protocols or even with itself. So what we want to achieve is so this is the ideal functionality, like an ideal RSP, and an ideal RSP is not leaking anything to Bob about A and B. Whereas this is the concrete protocol that we have implemented. So this ideal RSP is secure by definition because this is how I define the RSP. So in this framework, the abstract cryptography or the constructive cryptography framework, we treat cryptography from a resource theoretic point of view. And by that, I mean, what we want to achieve is to construct these resources, desired resources from a set of given resources. So let me explain this with the help of an example. So let's take the same example of one-time pad. So we have Alice and Bob. Alice wants to securely communicate the bit X, and she shares a secret key K with Bob. So she would just one-time pad this bit X with the key K and send this Y over authentic channel. And since this is an authentic channel, an eavesdropper would know this Y, but cannot manipulate it or change it. And on the other hand, since Bob knows the secret key, he can decrypt it and obtain the X. And this is the one-time pad protocol. So basically the size of X is the same as the size of Y. On the other hand, we have the ideal functionality, which we want to achieve is the secure channel where Alice sends X and Bob receives X. And so what we want to say is that we want to achieve this secure channel. This is the desired resource by using the secret key resource and authentic channel. And if we can achieve this, and by achieving, I mean, if I give these boxes, these gray boxes to any distinguisher or third party, and if just by looking at these boxes, he cannot distinguish whether he is in this ideal system or he is in this real system, then we would say that they are indistinguishable for all our purposes. And so right now, these are distinguishable. And why this is the case? Because on the right-hand side, we are leaking Y, whereas on the ideal system, there is no Y. So anyone who receives this box will clearly know that since there is no Y on the left-hand side, this has to be an ideal system. And so to make it comparable, we define a notion of simulator. And so the task of simulator is to relax this ideal system in such a way that it can make the ideal system indistinguishable from the real system. So simulator receives this size of this X, and it generates a random string of the same size, and it outputs Y. And now these gray boxes are indistinguishable. And so in this sense, these protocols are completely indistinguishable to any distinguisher, even a distinguisher who is information theoretically powerful, like unbounded. So, and that's why we can say that this is an information theoretically secure protocol, which is also composable. And why is it composable? Because for any protocol where I would use a one-time pad, real protocol, I could replace it an ideal functionality of it. And since any party interacting with either of these boxes cannot distinguish them, that means these are, and since this is secure by definition, that means this is at least as secure as the ideal system. So basically, we want to use the same idea to show security for RSP protocol. And what we show is that classical client RSP protocols cannot be secure in composable setting. So basically, we give a strong no-go result for all the classical client RSP protocols. And just to quickly sketch the proof, because it's a bit involved, so I'll just take a small example. So let's take an ideal RSP, which gives out the states from these four set. And what we want to show is that for security, we want to show a simulator that when receiving this plus theta on the Bob side can can make this protocol indistinguishable from the real protocol. This is what we want, like an ideal system to be indistinguishable from a real protocol. So we want to find a simulator. If we can find a simulator that that is indistinguished for any distinguisher, then we are done. But we show that if there exists for any simulator, there exists a distinguisher who would just simulate the honest Bob. So on honest Bob just takes the classical transcript and reproduces the plus theta state. This is what an honest Bob does in the real protocol. And this implies that there exists an algorithm where you could use the simulator and another pi tilde b protocol, which comprises of this honest Bob, which would generate a lot of plus theta, and then you can output a theta on the other hand. And this means that what we reduce this this security is to an algorithm that takes an input plus theta, which is unknown to the simulator, and outputs theta. And now you can make multiple copies of this plus theta. So basically, we would be able to clone these states if there exists a simulator. And this is independent of the protocol. So here I showed it for a particular case, but in the paper, actually, we show it for a very large class of families. And well, does that mean that the RSP is not useful at all? And it's not the case. So composability is not the end of it, definitely. It's good to have composable security because then we can just blindly use the ideal functionality instead of the real one. But if not, then we'll have to prove security by scratch for different applications. And so for this, we take two applications. One is the delegated quantum computing, which is the Bfk protocol, and we replace the quantum channel with this secure RSP. And we show that this protocol is still secure in game-based definition. And so for the game-based definition, we define it in the following way: that the server chooses server chooses two runs of computation, so two different angle sets, and sends it to Alice. Alice then tosses a coin and randomly chooses one of the computation run, and then she runs the computation with Bob. And in this way, we show that Bob is not able to distinguish which of the computation is run with Alice. And so we define a game-based version of delegated quantum computation, and on top of it, we also show that delegated quantum computation is also not composably secure. And this we do it by reducing it to, again, the secure RSP. But this time we use the no signaling principle instead of no cloning. So, so there are some open questions, is like what other kind of relaxations are possible to achieve composable security for delegated quantum computation. And also, our proof technique doesn't work for verifiable delegated quantum computation. So maybe composable security is possible in those cases. On the other hand, we use the same primitive for this quantum two-party computation. And the task in quantum two-party computation is we have a quantum Bob who has a quantum input psi, and we have a classical Alice who has some function f that she wants to compute on the side, and the output is f of psi on the Alice's side, and this is a classical output. And Alice and Bob only shares classical channel, and so we call this primitive oblivious quantum function evaluation. And the construction again goes through remote set preparation and the ideas that inspired from this Bfk scheme. And basically what we show is the security against malicious Alice in the simulation-based paradigm, whereas we could only show privacy against quantum Bob. And this is because we also show limitation with fully black box simulation by connecting it to classical proofs of quantum knowledge. And so if you want to have a simulator against quantum Bob, then we show that over a classical channel, this would reduce to a special case of classical proofs of quantum knowledge. And also one of the so the simulation-based security against malicious Alice was only shown for PPT Alice and not for QPT Alice. And again, this is because of the reason that so far we don't have quantum proofs of knowledge that have that can be used as a subroutine for multi-party computations. It's because the extractor doesn't have the probability close to 1, and we only have non-negligible probabilities for extractors of quantum proofs of knowledge. So this is a problem so far, that we don't know any protocol for proofs of knowledge in quantum case. And so this is still ongoing work where we are trying to go to a non-black box simulation setting and try to see if we can boost the security on both Alice and Bob side. And the open questions are definitely, what if we want to, how can we do MPC over hybrid classical quantum networks ultimately, and yeah, and the non-black box simulation. So this was a primary set of results are in this archive version. And so in summary, what we show is that secure delegating quantum functions is indeed possible. There's a trade-off. So with information theoretic security and computational security, basically perfect security is possible, but seems like it requires quantum channel. On the other hand, protocols based on classical networks are also possible, but they come at the cost of weaker security notions, like only against quantum polynomial time adversaries, and also a very large overhead. So the open problems are there any other applications of secure RSP apart from delegations? And also, can they be based on weaker cryptographic assumptions, or for example, just based on one-way functions, and or like, because that would optimize both the bring closer to practicality and would also make it more stronger. And so quantum computers, yeah, are definitely distributed around the world. So these are the numbers from last year on the active users on just IBM's quantum cloud. And so it definitely seems like algorithms and applications would soon require privacy, even on quantum cloud. So yes, thank you everyone for listening.
Thank you, Atul, for the nice talk. So I invite you to ask Atul any questions that you may have. So either feel free to unmute yourselves, or feel free to ask your question in the chat.
So two quick questions. One is just like my ignorance. How do you define classical proofs of quantum knowledge?
Yes. So there is a recent paper by Thomas Vivek and Tina Zhang, where they define classical proofs of quantum knowledge. And they also show that Mahadev's, so they also show classical proof of quantum knowledge for QMA and for a quantum money scheme, actually.
So
the way
like, a QCMA, because like you send just a classical proof string.
Yeah, so the definition is you have so the verifier is classical, and you have a quantum prover, and so the extractor uses the prover's unitary and UDagger, and it also applies some sort of single qubit operations for the QMA scheme. So it won't be
QMA, like it doesn't require any interaction at all.
No, yeah, it's QMA.
I see. So
because,
you send, so you don't send a quantum state; you send just like a classical string.
Exactly.
I see.
Because Mahadev's protocol can be adapted for QMA, like the verification.
I see. And that's actually related to the next question that I had, is that, like, it's been roughly 3 years since Urmila's like major breakthrough. have there been any indication that we can expect like a full analog of her work in the information theoretic setting?
You mean
I mean, like, does it seem like, is there any active, serious line of work towards getting rid of the cryptographic assumption in a protocol?
So right now, I know that a lot of people are trying to implement the Umilaw's kind of scheme experimentally. Theoretically, I don't know if there's any progress information theoretically. Yeah, that's a good question. I think we probably need techniques from maybe classical side, because quantum side there's not been
I always this impression that everything regarding like, I don't know, verifiable computing in the quantum world, it's always like lags 5 to 10 years behind the state of the art of like classical stuff, just because it's like there are so many hard complications, and these are things which have been figured out quite a long time ago classically. So yeah, just curious. Thank you.
That's true. No, I think, and also one of the interesting things in quantum is that the blindness in like this privacy is somehow linked with the verification, which is not the case classically.
Yeah.
So that's why I maybe a bit of progress on the delegation side might also improve, or like give some hints on verification. Yeah, there is yeah, and I don't know about information theoretic ones, but there is also a recent paper on verification for quantum sampling, where they boost verifiable protocol to blind, and with the constant round verification. But even another important problem that is open is verifiable quantum fully homomorphic encryption, even with computational assumptions.
Yeah.
This is not known. So yeah, there's I guess a lot of problems on this side.
Thanks, Tom, for the nice questions. I don't see any other questions. So I think let's thank Atul again for the very nice overview and for the nice set of open problems that he's posed. So thanks for joining us, Atul. Thanks for this very nice talk. Thank you all for joining. See you at the next seminar.
See you. Thanks, Atul.
Thanks a lot. See you.